Good morning, students. This is maths class. I hope all you are safe. See, in today's class, we are going to do the sums from exercise 2.3. In the whatever we learned in the previous class, that everything we are going to apply in this exercise. So we have learned that it obeys, complex numbers obeys associative law, distributive law, and then we have learned what is the additive inverse and multiplicative inverse. Once again, shall we recall it? The additive inverse of Z is minus Z, additive inverse. The same way, multiplicative inverse of Z is Z inverse. If it is for x plus iy, Z inverse, we have learned that is x by x square plus y square plus I into minus y by x square plus y square. This is what we have learned that in the last class. Additive inverse of Z is minus Z and multiplicative inverse of Z is Z power minus 1. And this, if it is x plus iy, we can write it x by x square plus y square plus I into minus y by x square plus y square. Say x plus iy into u plus iv. This either you can multiply by ordinary method or even we have a direct formula. See, this is xu, then only the real part, isn't it? See, then we know that when we multiply I into I, it will become I square and the value is minus 1. So, minus y into v. Then plus I into imaginary part is with multiply with the imaginary x into iv. So, we may get xv and this is plus y into u. Because why I am explaining again in the sense, sometimes in place of multiplying taking 2-3 steps, you can write directly. Or if you are multiplying also, no issue. Okay. Now shall we move to the problem? See the first problem. If Z1 is equal to 1 minus 3i, Z2 is equal to minus 4i and Z3 is equal to 5, show that subdivision 1 Z1 plus Z2 plus Z3 is equal to Z1 plus Z2 plus Z3. This is that associative law, isn't it? Associative law in addition. Okay, everything is given. I'm going to simplify first this one. So first we have to add which is given in the bracket. Z1 plus Z2. Z1 1 minus 3i plus Z2, that is minus 4i. What we may get, it must be 1 minus 3i minus 4i, that is minus 7i. Now totally take the left hand side, that is Z1 plus Z2 plus Z3. So Z1 plus Z2, the answer is 1 minus 7i plus Z3. Z3, the value is 5. So together the answer is 1 plus 5, 6 minus 7i. Keep it as equation number 1. Now, in order to find out the right hand side, first Z2 plus Z3. Z2 is given minus 4i plus Z3 is 5. So, only one real number and one imaginary part. So, more than that we cannot simplify. Now, totally if I take, that is Z1 plus Z2 plus Z3. Z1 is 1 minus 3i plus Z2 plus Z3 is minus 4i plus 5. Now we can simplify, isn't it? See, 1 plus 5, 6, imaginary part now, minus 3i minus 4i minus 7i. Taking it as equation number 2. See, both 1 and 2 is equal. So we can write it from equation 1 and 2. Z1 plus Z2 plus Z3 is equal to Z1 plus Z2 plus Z3. Simple only, isn't it? Now the second subdivision is associative law for multiplication. Subdivision 2, Z1 Z2 into Z3 is equal to Z1 into Z2 Z3. So solution, first to find out the left hand side we have to multiply what is Z1 into Z2. Z1 1 minus 3i into Z2 minus 4i. Shall we multiply? 1 into minus 4i minus 4i, minus into minus plus, 3 into 4 12, I into I is I square. We know that value of I square is equal to minus 1. So minus 4i plus 12 into minus 1, or first if we write this real part, that is minus 12 minus 4i. Now left hand side together, Z1 into Z2 into Z3, that is minus 12 minus 4i into Z3, the value is 5. Now multiply, that's minus 12 into 5, 60, minus 4 into 5, that is 20i. Again I am taking it as equation number 3. Now right hand side, Z2 into Z3, that is minus 4i into 5. So this is minus 4 into 5, 20i. Now Z1 into Z2 Z3, that is Z1 1 minus 3i into minus 20i. So 1 into minus 20i is minus 20i, minus into minus plus, 3 into 20, 60, I into I is I square. We know the value of I square is minus 1. So 60 into minus 1. So this is together minus 60 minus 20i. I can keep it as equation number 4. Now from equation number 3 and 4, Z1 Z2 into Z3 is equal to Z1 into Z2 Z3. Is that clear? This is what the first problem. Now second problem is, if Z1 equal to 3, Z2 is equal to minus 7i and Z3 is equal to 5 plus 4i, show that subdivision 1, Z1 into Z1 plus, Z2 plus Z3 is equal to Z1 Z2 plus Z1 Z3. This is distributive law, isn't it? Then the second subdivision is Z1 plus Z2 into Z3 is equal to Z1 Z3 plus Z2 Z3. So in order to complete this, first what we should do for the first subdivision, first we have to add Z2 Z3. Then with that answer we have to multiply. Keep that as equation number 1 and right hand side. First Z1 into Z2, then what we should find out, Z1 into Z3. Then add both. Keep it as equation number 2. Both anyway we will get the equal answers. Then we can write from 1 and 2. Is that clear? So I hope this both you can do it as homework. Okay, the second problem you can do it as homework. See, for the first subdivision, when you simplify both, you will be getting 15 minus 9i. Is that clear? For the second subdivision, you may get the answer as 43 minus 23i. 43 minus 23i. Check it. Okay, ma? Shall we move to the third problem? Okay, problem number 3. If Z1, Z2 and Z3, three values they are given. The question is find the additive and multiplicative inverse of Z1, Z2 and Z3. See, first we can write what is the additive inverse of Z. See, additive inverse of Z is equal to minus Z. Then multiplicative inverse of Z equal to x plus iy. Yes, Z inverse, isn't it? What is Z inverse if x plus iy is there? X by x square plus y square plus I into minus y by x square plus y square. Or even you can find it out like 1 by Z. Z inverse is 1 by Z. Using that also you can simplify. Since we have got a direct formula, we will use this. Okay. Now you can write additive inverse of Z1 is, what is that? Minus Z1, isn't it? So minus Z1, 2 plus 5i. Give the minus inside. Minus 2 minus 5i. Is that clear? Then additive inverse of Z2 is minus Z2, which is equal to minus Z2, the value is minus 3 minus 4i. So we may get 3 plus 4i. Okay. The same way the third one. Additive inverse of Z3 is minus Z3. So minus Z3, the value is 1 plus I. So when we give the minus inside, minus 1 minus I. So additive inverse for the 3 we have found out. Now we have to find out the multiplicative inverse. See, multiplicative inverse of Z1 is Z1 inverse, which is equal to, we have the formula x by, actually x1 the value is 2 plus 5i, isn't it? So we may get 2 by 2 square plus 5 square plus I into minus 5 by 2 square plus 5 square. So we can simplify. 2 by 2 square 4 plus 5 square is 25. This is minus I by 4 plus 25. So we may get the answer as 2 by 29 minus I by 29. Or you can take 1 by 29 outside. This is minus 5i. So minus I into 5 or 5i. So 1 by 29 into 2 minus 5i. Is that clear? Shall we do the second one? Multiplicative inverse of Z2 is Z2 inverse. Z2 in the question that is given as minus 3 minus 4i. Shall we use the formula? X by minus 3 by x square plus y square, minus 3 the whole square plus minus 4 the whole square, plus I into minus y. Here the value of y is minus 4, divided by minus 3 the whole square plus minus 4 the whole square. So we may get minus 3 by minus 3 the whole square is plus 9 plus 16, minus into minus plus. So plus 4i by 9 plus 16. This is minus 3 by 25 plus 4i by 25. So or else we can write 1 by 25 into minus 3 plus 4i. Both the denominator is same, no? That's why we have taken out. Okay. Now the third one is multiplicative inverse of Z3. As we know, that is Z3 the whole inverse, which is equal to Z3 is given as 1 plus I. So 1 by 1 square plus 1 square plus I into minus 1 by 1 square plus 1 square. 1 by 1 square plus 1 square, that is 1 plus 1, minus I by again 1 plus 1, or 1 by 2 minus I by 2, isn't it? 1 plus 1 is 2. So now we can take 1 by 2 outside into 1 minus I. Is that clear? See, in exercise 2.3, we have only 3 problems. In that second problem, I have given for you as homework. 1 and 3 is completed. Now we can move to the next topic, conjugate of a complex number. Conjugate of a complex number. See, conjugate of a complex number. The conjugate of the complex number x plus iy is defined as the complex number x minus iy. See, the conjugate, if it is x plus iy, we have to write it as x minus iy. See, it is denoted for z, we have to denote it as z bar. See, that's why I have written, simply change I by minus I. If it is, if z is equal to 2 plus 3i, z bar, the complex conjugate is 2 minus 3i. In front of the I, the symbol will change. Or if z is equal to 1 minus 2i, z bar is equal to 1. Here already minus I is there, isn't it? So it will change as plus 2i. Is that clear? This is what the conjugate. Say, here the product of a conjugate and the complex number. This is the conjugate and the complex number, isn't it? The complex number and its conjugate will always be a real number. It will always be a real number, on important note. Shall we check it? Whether we are getting again a real number or a complex number. So this is of the form a plus b into a minus b. So when we write, we will be writing a square minus b square. So here x square minus iy the whole square. That is x square minus I square into y square. But we know that the value of I square is equal to minus 1. So that is x square minus 1 into y square, or x square plus y square. So here there is no I. If there is an imaginary unit, we will say that as a complex number. But here there is no imaginary unit. So the product of a complex number and its conjugate always be a real number. Is that clear? So geometrical representation of z and z bar. See, if z is equal to x plus iy, x is real part and y is imaginary part, isn't it? X plus iy, somewhere here we may get it. That is, z is equal to x plus iy. Because both positive, so it lies in the first quadrant. Then, z bar means x minus iy, isn't it? So, x is positive, but this y is negative. So, we may get somewhere here. That is, z bar is equal to x minus iy. X positive means this is the positive line, isn't it? Y alone, that is negative. So, negative side I have taken. So, always we used to get like this. Okay. See, this conjugate is always useful when we are dividing by a complex number. Say, rationalizing the denominator. Are you remembering? If it is 1 by 2 plus root 3, what we will do in order to simplify, rationalize? We will take the conjugate 2 minus root 3 by 2 minus root 3. That is in order to remove this root. The same way, if it is 1 by x plus iy, the conjugate we know. In front of I only we should change the symbol. X minus iy by x minus iy. x plus iy into x minus iy. We know the answer is x square plus y square. Directly we can write x square plus y square. Here it is x minus iy. So the denominator, now there is no complex number. So the conjugate is normally used in this divisions. Okay. Now we are going to learn some of the properties of the complex conjugate. The properties of complex conjugate. Z1 plus Z2 the whole bar can be written as Z1 bar plus Z2 bar. The same way Z1 minus Z2 the whole bar can be written as Z1 bar minus Z2 bar. Now Z1 into Z2 the whole bar is equal to Z1 bar into Z2 bar. Now Z1 by Z2 the whole bar is equal to Z1 bar divided by Z2 bar. All when it is together, either it is addition, subtraction, multiplication or division, we can separate the conjugates. Okay. Here Z2 is given not equal to 0. Why? If it is 0, it is infinitive. There is no value. That is why they have given Z2 not equal to 0. Then real part of Z is equal to Z plus Z bar divided by 2. Real part of Z. Imaginary part of Z is equal to Z minus Z bar divided by 2i. Then Z power n the whole bar is equal to Z bar the whole power n. N is an any integer. N is an integer. Now Z is real, means Z and Z bar will be equal. Z is real means if and only if Z equal to Z bar. The same way, if Z equal to Z bar, we can say that Z is real. Now, Z is purely imaginary if and only if Z is equal to minus Z bar. If Z equal to minus Z bar, we can say that Z is purely imaginary. Then, Z bar the whole bar equal to Z. See, we will be learning some of the proofs. Okay, some of the properties we will be verifying. Some properties, these properties are important 2 mark questions, 2 mark or 3 mark. Okay, this proof they will ask in 2 mark or 3 mark question. That's this 8th one and 9th one. Some of the proofs we can learn. Okay, for example, the first one's proof we can learn. See, this is the first one, right? For any two complex numbers Z1 and Z2 we have. Okay, I am taking, let Z1 is equal to x1 plus iy1 and Z2 is equal to x2 plus iy2, comma, this x1, y1, x2, comma, y2 all belongs to real numbers. Now, shall we find it out? Z1 plus Z2 the whole bar. See, Z1 actually that is x1 plus I into y1 plus Z2 is x2 plus I into y2, the whole bar. So, first here I have to add it. So, shall we add? What we may get it, my x1 plus x2 plus I into the imaginary part y1 plus y2, the whole bar. Now this is real part plus I into imaginary part. Now we can find out the conjugate. Conjugate means just change the symbol of I. So we may get x1 plus x2 minus I into y1 plus y2. Okay, now if I separate it, see, x1 plus x2 minus I into y1 minus I into y2. Now I am combining together. x1 minus I into y1 plus x2 minus I into y2. Actually, this is the conjugate of z1 and this is the conjugate of z2. Isn't it? So, z1 plus z2, the whole bar we have got it, z1 bar plus z2 bar. In general, z1 plus z2 plus etc. plus zn, the whole bar can be written as z1 bar plus z2 bar plus etc. plus zn bar. Is that clear? The same way we can prove for multiplication, subtraction and division. Okay, that's left for you. If you want, you just try to do it. See the next property, a complex number z is purely imaginary if and only if z is equal to minus z bar. Important. Okay, see, I am taking, let z is equal to x plus iy. Then what is z bar? We know that is x minus iy. So either we have to take the first condition, if and only if, isn't it? So both we should prove. Now I am taking if z is equal to minus z bar. Okay, z is equal to minus z bar. What happens? This is x plus iy equal to minus z bar is x minus iy. So this is x plus iy equal to, give the minus inside, minus x plus iy. Bring all the terms to left hand side. This is plus x. This is minus iy is equal to 0. Plus iy and minus iy will be getting cancelled. So we may get 2x is equal to 0 or x is equal to 0. See, in this complex number, if x equal to 0, what happened? Z is purely imaginary. Yes or no? When x is equal to 0, automatically we will get, which implies z is purely imaginary. Yes or no? So this only they have asked us to prove also. Now in the reverse part, if I go, z is purely imaginary means only we have imaginary part, that means x is equal to 0, isn't it? So x equal to 0 implies 2x also equal to 0. So when 2x equal to 0, even I can write x plus iy minus iy. I can take that to right hand side. So this all we can get when z is equal to minus z bar means z is purely imaginary. The same way, if z is purely imaginary, we will get z is equal to minus z bar. Is that clear? See, in today's class we have did exercise 2.3 and we have learned few properties of complex conjugate. For z, the complex conjugate is z bar. Just change the symbol of I, isn't it? This is what the new thing we learned, and one homework is given. Complete it. See you in the next class. Thank you. Bye-bye.